about me talking about NV centers, but then when I saw further Zhelezko on the list of speakers, and so I decided that no, further is going to do a complete and marvelous job as he always does, and I really enjoyed his lectures. There will be some NV centers, but now I have to really watch what I say. Yeah, that's good. All right, no problem. All right. And like I said, okay. And various other directly and loosely related topics, okay? So my plan tentatively, okay, if you like this idea, is that today I'll give you like a broad overview of this field that I find quite exciting, the zero, oh, I have to learn to use this as delay, the zero to ultra low field NMR, and I'll tell you why we do it and what are the applications and so on. So I'll give you a broad overview. I thought that hour two, we can discuss the fundamentals of this. It's not so convenient. That's okay. I'll learn. Okay, in the hour three, we'll talk maybe, if you like, about elephants. And here, it's not going to be biophysics. It could be biophysics, but it's not going to be biophysics. It's going to be about the elephants in the room of modern physics. So we have some huge problems like dark matter, with a big elephant in the room. Is like the most of the mass in the galaxy, and we don't have not a faintest idea what it is. We have some very interesting hypotheses, and that's what I wanted to maybe talk about in hour three. We'll see. And then in hour four, I really don't know, but maybe we can talk about some things that our group does with NV centers. And recently, it's a demonstration of a gyroscope based on NV centers, which will give us a chance to also remember how these guys work a bit without repeating what further said. All right. So, you know, if you say NMR, most people immediately think big magnet, okay? And in our case, we are sort of people inside out. We do everything opposite to what normal people do. And so instead of a magnet, we actually have a multi-layer magnetic shield. So not only we don't apply a strong magnetic field to do NMR, even the Earth field is very strong. So we take a serious effort here to shield it. Okay. And then you have to do everything different from NMR, so from the usual NMR. And the usual NMR detects signals normally by Faraday induction. And this idea is that you have nuclear spins that are due to nuclear magnetism, like a magnet. And if you put these spins perpendicular to the leading field, they precess like this. And so if you put a coil perpendicular to this leading field, the magnetic field or magnetic flux from these nuclear spins would change the field in the coil, and that is Faraday induction d phi dt, and that's the signal in normal NMR. And by the way, the bigger the signal, the bigger the field, the bigger the signal for two reasons. Normally, you use thermal polarization, so the bigger the field, the more spins you have, but also the frequency of rotation is proportional to the field. And so because this Faraday induction is d phi dt, and d by dt is omega, it's another power of magnetic field. So normally signals in NMR are proportional to b squared. So you know, when we started telling people, you know, we're gonna do NMR at zero field, they were ready to call ambulance, you know, on us, because okay. But anyway, we can't rely on Faraday induction if we work at zero field, because everything is very slow. So we need some other sensor. And actually, this what led me to this field, because I was working on developing atomic magnetometers, vapor cell magnetometers. And so it used to be that we made them ourselves. I'll tell you Now we try not to do this, and I'll explain why. But the atomic magnetometer is actually a fairly simple device. It has a vapor cell, usually containing alkali metal, and then we had a couple of lasers, one laser to optically pump or polarize the spins, and then the probe laser to see what the spins are doing. And this is the idea of the magnetometry with atoms. So you polarize atomic spins, it's not nuclear, atomic, or most of it. This is the electrons have the big magnetic moment, so they are the sensor here. And then if they are exposed to magnetic field, they precess, and we detect that optically also using the probe laser. Okay, so here we still to do such an experiment, we still need to polarize the nuclear spins, right? And like I already said, in normal NMR, you just stick your sample in the big field and you wait for spins to thermalize, and then a tiny fraction, typically 1 in a million or something, they like to point a little bit more along the magnetic field than opposite, and then you use this beautiful fraction of speed. So I don't like thermal polarization, and I try to not use it, but sometimes it's the very easy thing to do so. So still, here I'm showing you this kind of a bit of a cheating here, because above this shield we do have a magnet. I'll show you many examples how we don't use magnets, but here for this experiment we do have a magnet, and this is so-called a Halbach array. This is a magnet you can either make or buy not too expensively, and this gives you 1 to 2 Tesla field. So in this experiment shown, you put the sample in the magnet and let it sit there for like 10 seconds or something, let the spins pre-polarize, and then you drop it, and then you measure it, okay, here. And the molecules, okay, so the initial experiments were all done with exceedingly simple molecules like this kind of formic acid molecule here. This is a bit special, you know, that most of the carbon atoms in nature are C12. That's the most common isotope, and it has 0 nuclear spin. So if you want a non-zero nuclear spin, you have to use carbon-13, and naturally it's only 1.1% of this isotope, but you can buy in the catalog so-called labeled compounds where you have more of this C13 to enhance your signal, or you can work with natural samples, natural abundant samples, but then you only have 1%. It's like effectively diluting your sample. What else can I tell you? Yeah, it's room temperature. Yeah. So this is the zero field regime is quite unusual. So if you talk to NMR spectroscopists and they would like to tell you about the theory of NMR, and they will of course use a Hamiltonian, okay? And in a Hamiltonian, you have this it's an energy function, right? And you have the hierarchy of terms. You have some terms that are larger, and then there are some terms that are smaller. And that's how you look at the typical NMR Hamiltonian, and in a strong field, the Zeeman term, the big energy, is dominant. And it's nowadays people have 20 Tesla magnet. For protons, you can talk about gigahertz or something. Precession frequency. Okay, so then on top of that, there are in addition to this, now there are some smaller things, like for example chemical shift. So depending on the chemical environment, there is a different slide shielding of the external field, and the unit of this chemical shift is ppm, part per million, which tells you that's a tiny thing. And then there is chemical shift anisotropy and so on. And so the last poor relative term, the smallest one in this huge hierarchy, is so-called J coupling. And I'll explain to you more, but this is basically coupling between the dipole moments, nuclear dipole moments, in the molecule, but it's a funny one because as we'll discuss in detail later, if if you are working with a liquid, for example, or a gas, the molecules tumble like crazy, and the normal dipole-dipole interaction that we are used to, d1 vector dot d2 over r cube, that averages to 0. And what we work here is this so-called scalar J coupling. It's a very obscure terminology, but people were really surprised to see that actually the dipole-dipole interaction doesn't completely average. There's a tiny residual thing. And for experts in atomic and molecular physics, I can tell you right away what the explanation is a second order hyperfine interaction. And it doesn't have the angular dependence of the normal dipole-dipole interaction, so it survives the averaging by tumbling. And so this term, so I said that the main term in high field NMR is like gigahertz if you go to frequency units, and here we are talking about typically 100 hertz for a carbon and a proton, not so far away in the molecule from each other. We're talking 1-200 hertz kind of strengths of the interaction, gigahertz, 100 hertz. Okay, and now if you go to zero field, so then you have like social inversion if you want. So the poor relative, that is this tiniest thing, is now the king. It's now the main interaction. And so now we don't actually talk about individual carbon-13 or proton spin, actually, right? We now classify them as a total angular momentum. So this is spin 1/2, this is spin 1/2. You add spin 1/2 and 1/2, you get either 0 or 1. I hope I don't have to explain to this audience how to add two spins 1/2. And so these are actually the states that we, this is too high tech for me. I have to point in a very weird direction. So, okay. You have f equal to 0 and f equal to 1. You know what? Right. And so we have those states. And so when we drop the sample, we have, well, okay, I'll tell you more details how this is done. But if you have somehow the coherence between this f equal to 0 and m sub f equal to 0 in the f1 state, there is an oscillation. It's picked up by the magnetometer. You have a nice signal. It's a small signal. Okay. So it's like you know, if you're really lucky, you can have a picotesla or something. But yeah, it lasts for seconds, and so it's a nice kind of magnetic resonance here. All right. So now, yes. You know what? This is a one-way. You only go forward here. So it's, what about this one? Yes. I figured it out. Okay. So sorry. I got it. It works. No, it's fine. It's fine. Yes. Question. So because the signals from the sample are small, we have to get rid of the noise, and that's why we have the shielding. But not only that, we also, in order to really have this J coupling be dominant, we also have to get rid of the Earth field, because we work with 10 to minus 3, 10 to minus 4. We will, okay, so now what we're going to do, we're going to actually apply magnetic field and start splitting those sublevels, as you will see on the next slide. But these are really tiny fields. Sorry. Yeah. Yeah, sometimes there's the inner layer. Sometimes it's ferrite, and this is done. Ferrite is not such a good shielding material as metal. On the other hand, it's an insulator, so it doesn't have the Johnson noise, the noise of the shield itself. So sometimes we do that. Yeah. It's the so if you have the coherence, there's a beating, or you can say the two spins, they kind of, I can't say precess, but they do some funny things. Yeah, so you can say precess one with respect to the other, and that creates external magnetic field that's changing, and that's magnetic field picked up by the magnetometer. Yeah, the magnetometer is this object over there. So it's a vapor cell. So this blue thing is the sample, and the magnetometer is right next to it. It's a vapor cell, and then there are laser beams for the operation of the magnetometer. So I'll tell you about very sort of down to earth applications of this thing, but before we go down to earth, let's go in the galaxy. And so one application of this is the dark matter search. And in order to explain how we use zero field NMR to search for dark matter, I will need to disclose some key ideas in this, with more details relegated for the elephant hour, so to say. So one of the paradigms, one of the ideas for what dark matter could be, and I emphasize, even though you will see people who are proudly beating themselves on the chest and telling you all kinds of things about dark matter, these are all hypotheses. We don't know actually, and there are very, very different and alternative pictures of what it may be, having very little to do with each other. And within every paradigm, there is an internal logic that tells you, if for instance, I will show you one example of this, how if you assume that that dark matter is very light particles, then we will infer the spin of these particles and coherence time and so on. So within one paradigm, you can know, but you don't know whether this paradigm has anything to do with reality. But one of the dominant model is that dark matter consists of some particles. Usually people talk about WIMPs, WIMP, which stands for weakly interacting massive particles. And this could be a particle with mass, say, on the order of the mass of the proton. It's some GeVs in energy units, and then they somehow live in the galaxy. They interact very weakly, and then when they come here, we would look for them using a particle detector. So we don't take the detector to an accelerator. We take it actually underground or under a mountain to reduce the backgrounds, and then we look for tracks. Okay, so this is sort of the dominant thing, and people have been looking for it for many decades, and this is a totally possible scenario. But there's another paradigm, which is that dark matter is actually made of extremely light particles, and I will tell you how light they could be. Well, I can tell you now. So the proton is a GeV mass. Okay, if you mc squared converts you energy to mass. So I'm using frequency units always. And these particles could be down to 10 to minus 22 eV, anywhere in this from GeV to 10 to minus 22 eV. And if you have a bunch of bosonic particles that are very light, and there are many of them, then sometimes it's easier to not think about them as particles. If such a light particle hits anything, it doesn't leave any track or anything like this. But it's when you have a lot of bosons in one place, they form a field. It's like when we have, for instance, radio waves. Very rarely we need to remember that they are actually made of a lot of photons. It's easier for us to talk about the field, and the way we go about detecting radio waves. We don't make a particle detector and look for a track. It would be really stupid, right, to look for a track from a radio frequency photon. So we do is some kind of collective effect. We make an antenna and we look for induced currents. And so this is the same idea here, that dark matter could be a classical field. Okay. Now what? This thing is not a friend of mine. Also it's still weakly interacting with normal things that we're used to. So for instance, it would ignore our shielding. It would just go straight through the shielding. If nevertheless we see the photons are massless, but if these bosons that constitute dark matter do have mass, then this corresponding field, according to the equations that govern such particles, Klein-Gordon equation specifically, this field will not be static. It will oscillate everywhere at the Compton frequency. So basically at the frequency given by the mass of the particle. This is funny, actually, because, okay, if a particle, let's say, is 1 electron volt, then it's like 10 to the 14 hertz. Okay, it's fast as but if it's 10 to minus 22 electron volt, this oscillation will be 1 over year, right? So it's 1 oscillation in a year. So, okay. And we don't know where it is. So there's a lot of parameter space to explore. As I will explain to you, this is like really interesting, that if you assume that this field is really bosonic, okay, like this, like I'm describing. So this picture in its logic leads you to say that the coherence time of such an oscillator, so how many oscillations it will take to forget the phase, should be relatively long. The Q factor is 1,000,000 or something, and means that delta nu over nu is 10 to minus 6. It's kind of amazing, but I'll show you. You will see that elementary considerations lead to this. And one of these possible ultralight particles is called axion. And so some years ago, we thought of an experiment that's now a reality, which is a cosmic axion spin precession experiment, or CASPER. I need to mention to you something funny. So Frank Wilczek is the Nobel Prize winner, who is one of the founding people in the axion business. And in his Nobel lecture, he recalls a story about how he named axion. And you would think, okay, axion sounds scientific, muon, pion, and then maybe it has to do something with axial currents or something very scientific. No, this is named after a popular US cleaning fluid that you can buy on the shelves. And the idea was that the reason people introduced the axion is to solve one of the puzzles in physics, actually having to do nothing to do with dark matter. It's a so-called strong CP problem. I'll explain later. So it was introduced. This idea was introduced to clean up a problem. That's why it's axion. And later on, people realized, oh, wait a minute, maybe we can kill two birds with one stone. Maybe it could also be a nice dark matter candidate. And so, yeah, we'll look for it with this experiment based on NMR. And so again, I show you the same picture. And now let me walk you through how this dark matter search works. So if you, so now I changed the axis, so my transitions are like this, like a V system here. I didn't change anything physically, just changed the axis labeling. But anyway, in the absence of any external field, there is one line in the spectrum. Okay, so this is your J coupling frequency. It's about 220 hertz or so. Now, in this shield, we have coils, so we can apply a little bit of a field, and this would be 100 picotests, something tiny. And when we do apply the field, those Zeeman sublevels of F equal to 1 split due to the Zeeman effect. And so if we look at the spectrum of the NMR spectrum, now we have a doublet. We have two lines. So it's on average 220, and we split it by a few hertz, if you like. Now, imagine that on top of this little bias field that splits the magnetic sublevels, we also add some modulation. Then what will happen is that these sublevels will be wobbling, going up and down a bit. And so if we look at the NMR spectrum, it means that each line will acquire a series of sidebands. For frequency modulation, it's a Bessel functions. There are many of these sidebands like that. So the idea of the dark matter search is that we play with our system, we apply this oscillating field, we calibrate the system, then we turn it off, the oscillating field. And one of the possible interactions of these axion-like field is that it would act like a quasi-magnetic field, do the same thing as the magnetic field. So we turn off the modulation, and we still look for sidebands. So that's the idea. But here we have a bit of an issue because I said that the dark matter field is coherent. Okay, and so if we are looking at let's say a field at 10 hertz, for example, right? Something like this. Then the coherence time would be 1/10 of a second times a million, 10 to the 5 seconds. And 10 to the 5 seconds, so 1 year is pi times 10 to the 7 seconds. Actually, with a great, with 3 or 4 digits, it's really pi times 10 to 7 seconds. Very nice coincidence. So 10 to the 5 is like a month or something. No, wait a second, not a day, right? A day, sorry. It's a day, it's a whole day. But each of these experiments, little experiments, are only about 10 seconds because of the finite coherence time of the molecule itself. NMR signal only rings for 10 seconds. And you might think that this puts your search in great disadvantage because you have this nicely coherent dark matter field, and now you're going to waste all this beautiful coherence time. But this is very interesting because we also work with NV centers, and in NV centers, people encounter this problem all the time, and it has been solved by something that's called correlation spectroscopy. And so we implemented correlation spectroscopy to take the full advantage of the coherence time. And it is a bit funny because, of course, correlation spectroscopy or some ideas like that, they were not invented initially for NVs, they come from NMR. And so now it makes a whole circle back. So the idea here is that if you do have a stable reference oscillator, in this case, it would be dark matter playing that role, Then you can just do your individual experiments, and you write down, the time when you do the experiments, and then you can add an appropriate phase shift and then average everything coherently. The problem here is that you don't know at what frequency dark matter goes, and you don't know what the phase is. And you might say, oh, this doesn't work. But it does work because we have nice computers. And so what we can do is we can just put all these into the computer and try all the possible phases. And as we've done with our here calibration experiment, if you do this procedure, so if you have zero phase adjustment, you have these very large signals that are sort of your carrier. But now at a certain phase, the carrier at any phase other than zero, the carrier disappears, but your unknown modulation sort of comes up at one of the phases. And so you can feed this data in the computer, run the analysis, and then basically do the search for dark matter. You just look at this picture, and if there are these unexplained peaks, maybe it's dark matter, and maybe if somebody is listening to the radio next door or something. Or actually, in this case, it's even it's not about the radio, it's more like snoring, because it's like a few hertz, so what they okay. Right. So that is all fine, and that's for okay, sorry. And that is when you're looking for frequencies that give you sidebands that you can actually separate from the central line. But if you want to go to really low frequency, detect really low frequencies, there are, sidebands don't separate from the central line or from each other, and they sit on top of each other, so you can't really look for them. So it's a problem for low frequency. But if you think about, say, back to this picture, what a low frequency does. So you have the splitting of these Zeeman sublevels, and then the dark matter adds a little bit, right? And then goes back. It's very slow, like this, right? So it's basically a slow drift, effectively, of the field. So you can look for that. The problem you immediately encounter is that no matter how good a shield you do, ferrite or whatever, there are some drifts, and they are significant. And so it's very, very difficult to separate your real dark matter signal from drifts in the shield. And this is a common problem in precision measurements. If you're looking for tiny effects, and then there is some, magnetic field drifts, how do you separate? And the idea in this business is that you use a device called comagnetometer, which you stick in the same place where you're trying to measure. And the comagnetometer, you choose the system that is not sensitive to the exotic effect you're looking for, but it is sensitive to magnetic field. And then you compare your actual sensor that is sensitive to both magnetic field and the exotic effect to something that's only sensitive to magnetic field, then you can separate. The usual problem with comagnetometers is, can you really locate them in the same place? Do they really see the same field? Or maybe there are some gradients, and your comagnetometer is measuring one thing and your sensor is measuring the other. So in order to address that, we had this idea that why don't we put the comagnetometer right at the same molecule that we use to look for dark matter, and it's acetonitrile in this case. And the point is that inside, if you look at the spectrum now, it's a bit more complex spectrum. There are two families of lines. So one family is around 140 at J and this J coupling interval, and then the other group is at twice that, 2J, at about 280. And if you now work out the relative sensitivity to magnetic fields and dark matter, you find that it's different. So this gives you a very nice way to have a magnetometer right there in the same place at the same time, acquire all the spectra at the same time. And so we've tested this for various possible systematics, and we found that it works really, really well. And so we used it to constrain dark matter. And so as a result, we published actually 2 papers, one this sideband search and another this magnetometer search, and they cover this different range. So when you talk about dark matter, this is a very typical kind of a plot you have. So here you have the mass of the particle, and on the top you convert it into frequency. So whatever you want to use. So the masses, as we said, go from 10 to minus 22 to very, very high. In this case, we explored a small fraction of that, but so 10 to minus 13 is about 10 hertz or something, and that's 1 over year. And so this was the sideband search, and that was the magnetometer search. So that is one application. Do we what? Yeah, it's stable, and so sort of the magnetic field, for example, drifts we take out, so we don't care about them. Yeah, so for instance, you're saying with the J coupling itself, for instance, can be changing with. Yeah, I think at some level, this is also gonna break down, but at the level that we studied so far, that was not a problem. But yes. More questions? That's a very good question. Yeah, so this was nice, and actually this experiment still used thermal polarization, that magnet that I talked about, and then we were very excited about improving this almost immediately by about 4 orders of magnitude by using the techniques of hyperpolarization. That I'm going to tell you about those. But now I think it's no longer needed, because there are 2 groups that have already done this with different techniques. So this drew attention to this parameter space, and actually one of the groups is run by this young fellow by the name Jiang Min at the University of Science and Technology in Hefei. He's known by the name Billion, actually, more than Jiang Min. But so Billion spent a lot of time in our lab, and then went and built a beautiful device called spin amplifier and a maser, different devices at Hefei. And so now some of these experiments we're actually running in his apparatus in China. All right. So now I would like to tell you about some new directions in zero field NMR. As I mentioned, I don't like thermal polarization. I really like hyperpolarization. And there are many different clever things that have been developed in recent years. So, one idea, and maybe I'll tell you, I hope I'll tell you more about how this works, but it's using parahydrogen. So it turns out that if you take hydrogen gas and you cool it simply, then if it reaches equilibrium, it's in a singlet state. So the spins are highly ordered. And then if you have some kind of a chemical reaction or virtual chemical reaction, you can transfer this order onto the spins you want to measure. And that can result in very high degrees of polarization. So we are very excited about this and pursuing this a lot. Then there is a technique called dynamic nuclear polarization. And here the idea is that, you know, the spin of electron has a 10 to the 3 times higher magnetic moment than the nuclear spins. So you can actually, if you cool things in a very strong magnetic field, you can actually fully polarize electrons. And DNP is a trick of how you take this high electron polarization and then transfer it to nuclei. We have a colleague at the University of Lyon by the name Sami Janin, and he has this beautiful DNP apparatus. And so we took our machine, portable ZULF machine, took it there, and now we have a combination. So this is going to be published soon, a combination of this classic DNP and ZULF. Then there is something that is named similarly called KIDNIP, or chemically induced dynamic nuclear polarization, but it's a completely different thing. You know, the name is the same because people who first saw it were a bit confused about the mechanism. but this is actually a beautiful thing, which is you take your sample and you shine light on it, and out comes polarized nuclei in a very high concentration. I'll tell you about that. So these are the most exciting things for me, combining various hyperpolarization techniques with this NMR. In the meantime, there are developments in sensors, and I told you that, you know, how I got into this field. We were building these sensitive magnetometers, but now there are several very nice companies that make basically state-of-the-art magnetometers. It's hard to make a homemade magnetometer that is as possible, but, you know, and so it's much easier now to just buy a commercial magnetometer, stick it there and use. That's what we do. Then diamond may have advantages, and we have one direction that is, we think is very promising, and that, so diamond at the first glance would look like a really bad sensor compared to atomic magnetometers. Many others will make it worse, but it has this advantage. One of the advantages is that it can have atomic spatial resolution. So that's not something it's very hard to do with a vapor magnetometer, but a diamond magnetometer can allow you to measure things on atomic scale, and that's I think is the most promising direction. Then there are other things like anisotropic magnetoresistive magnetometers that are good enough now to measure NMR signals, and that will probably also give another boost to this field. So in conjunction with these developments, then various techniques are correspondingly being developed, such as polarization transfer. So you, for instance, have polarized protons, and then when you want polarized nitrogen or polarized carbon-13, and there are pulse sequences, pretty sophisticated, that allow you to move the polarization where you want, or maybe you have polarization on one part of the molecule, and there's kind of a spin chain, and you want it in another place, or maybe you want an entangled state, something like that. So this is all possible. Then there's microfluidics. When you talk about small samples, it's a beautiful thing, you know, the way I think microfluidics, we all know electronic chips, right? So it's some little box, and then there are these wires. So microfluidic chip is the same, except for instead of wires, you have a channels for fluid. And then you can do chemical reactions or whatnot. That's a beautiful thing that's being combined with the zero field NMR. And then there's it's a recent proposal that we are now pursuing together with my colleague at CERN, Magdalena Kowalska, and others. It's detecting ZULF NMR by radioactive decay. The idea is that if you actually have a radioactive decay, then you can detect a single event. So you can have very high sensitivity these days. And this is combining some advantages of NMR with very high sensitivity of radioactive detection. And so now having this stuff available, there are applications and single spin, single molecule ZULF NMR. So we already heard from further about the single spin magnetic resonance measurements, but what we would like to add to this is a zero field, and I call this extreme NMR. You know, everything is at the extreme. So that's still in progress, but should be possible. Then there is chemical reaction monitoring and catalysis. May sound very prosaic to you, but it's very important. And here, ZULF zero and ultra low field NMR has a big advantage, because if you work at low frequencies, the skin depth is even in a metal is very large, and so you can actually look inside metal containers and see what's going on in them. And for chemical processes like catalytic reactors, for example, it's very important. So it's a big advantage. Also, high field NMR really cares about susceptibility uniformity. If you have some kind of heterogeneous material or something that leads to immediately to line broadening, we don't care about this at all. Not at all. And so that's another advantage. Quantum control, that is maybe related to this. So there are interesting things you can do, like quantum computing type of thing can be done also at zero field, and it looks very differently. I'll show you one slide about that. Now we're also moving to working with biomolecules with an obvious application to health. And dark matter we already discussed. And then there is another application, possible application is battery diagnostics. Also, maybe not doesn't sound so exciting, but very important these days. And this is a concept drawn by my colleague John Blanchard. It's using NMR to search for dark matter, right? But of course, it's all wrong. It's not a high field spectrometer in this case. It's a ZULF spectrometer. So we need to draw something else instead of a big magnet. Anyway, it's a nice picture. So zero field NMR was quite a bit of a fringe. So it was first sort of this idea was put forward by Professor Alexander Pines at Berkeley. He is a famous magnetic resonance guy. And one of his students blew a superconducting magnet. And Pines was mad and said, so now you will have to do a zero field. And indeed, they started thinking about it and realized the susceptibility advantages and so on. And so it was a bit like of a curiosity. And how people did it, they did what's called field cycling. They put a sample in a high field, polarize it, then they bring it to zero field for some evolution kind of period, then they take it back to to high field. You'll see we still do something like this sometimes as well. They take back in high field, you measure it there. And then squid magnetometers, superconducting magnetometers came about, and Pines hooked up with another professor at Berkeley by the name John Clark, who is a pioneer of squids, and they have done really beautiful work, including detection of J couplings and so on. And in the meantime, about that time, there's like 15 years ago, maybe even something like that. Yeah. Pines calls me up, and I was then working at Berkeley on atomic magnetometers, and I didn't know anything about it. And he said, "Come, we need to talk." I come to him, and he says, "Why don't we measure NMR with atomic magnetometers?" I said, "Okay," and so we started a discussion. Also, another person, Andreas Trebesinger, Pines postdoc, was involved, and we started doing things. And at first, it was really, really painful. The sensitivity was not enough. It was hard to get the signals. It was hard to imagine that it will ever be practical, but it was improving. And then so after 10 years of development and trying different things and doing microfluidics and micromagnetometers together with John Kitching at NIST and company. So it started to be more and more practical. And eventually, I think now it is sort of a legitimate and recognized field of NMR. And one sign of this is that a few years back, we were able to convince the Marie Curie organization that this is a good topic to have this ITN, Innovation Training Network, like yours, I guess. Yeah, is yours ITN also, or some other? But there's a similar idea, and so I think this basically seals the deal, because now there will be about 12 people getting PhD in ZULF NMR. 2 of them are here in the audience. So now I think it's basically when young people get their PhDs in something, PhD is what you learn during your PhD is something you carry till till the end of your career. Anyway, we had a lovely meeting in 2019. Now this program is coming to the end, but it's been a great success. Yeah. Right. So I guess. Okay. Then I tell you more at some point, but we have like a couple minutes left. Maybe you guys have questions.
Anyone?
Yeah, thank you for the great talk. I'm curious about this line with you showed for the dark matter. I mean classical dark matter field. You said you were looking for line width of 10⁻⁶, or Q factor of 1,000,000. I have not understood where this comes from. Is it about
because it's good that you haven't understood, because I have not explained it. I will explain this. It takes 5 minutes to explain, and I'll do this when we talk about the dark matter logic. Yeah.
Any more? Okay, so I guess this session ends here, and we can go for coffee break.
Thanks. It's okay. I got used to it. I got a hang of it in the end. It's just the design.
Maybe next time just use. I have a question.
Yes.
So you showed this one graph of